We present VIRDO, a visio-tactile implicit representation of deformable objects. Deformable objects are prevalent in our day-to-day lives. However, they have received less attention than rigid bodies due to complexities in modeling, state estimation, and controls. The research goal of our project is to derive a deformable object modeling that has visio-tactile representation that predicts geometry and contact, and is compatible with common robotic sensors. At a high level, VIRDO decomposes object representation into a pointwise deformation field and nominal shape representation. The nominal shape is the geometry of an object in the absence of external forces. Here, we visualize architecture of our model. As in the left panel, the inputs are reaction forces at the wrist, partial point cloud of object, and contact locations. The right panel shows the geometry of the object reconstructed from our implicit representation. VIRDO architecture has two main components, object module and deformation module. The object module constructs nominal shapes and is conditioned on object code. The deformation module produces deformation field and is conditioned on both object code and force code. Here is our model representing various deformable tools and their contact formations. We used only one model for all these reconstructions. When trained, VIRDO learns how to bend nominal shapes given a contact formation. With the same contact location, VIRDO outputs unique deformation fields given different reaction forces. Then we tested VIRDO's generalization ability to unseen contact location and unseen reaction force within the distribution of training dataset. We found that VIRDO can predict deformations with high accuracy, which is a desirable feature in robotics applications given a wide variety of interactions. We also tested the model's ability to infer a deformation field given partial information seen from the training. Given reaction force and object code, the model makes initial guess on deformation field fairly close to ground truth. This shows VIRDO's ability to perform state estimation when the vision is missing. Using the partial point clouds, it updates contact embedding by minimizing the mismatch between the initial guess and the partial observation. With our loss function, VIRDO can infer dense correspondence without explicit supervision. In this figure, we first paint a nominal shape and track the painted points by applying a variety of contact formations. Maintaining correspondence is important for tracking a pose and relative deflection of a specific point during robotic tasks. Finally, we visualize these embedding spaces using UMAP projections. Object codes exhibit significant separation as in left panel, however, as in the middle panel, force codes are distributed according to their bending direction. This suggests that the force code clusters similar deformations generalized across different objects. The right panel shows when two latent codes are concatenated. We found that the model learns to cluster latent features by deformation properties, such as stiffness, that are not directly observed or given as input.